In this video presentation, we will be learning about the RBF called Radial Basis Function Networks under the topic Feed Forward Neural Network. These are neural networks based on radial basis functions. The structure has three layers, namely input layer, hidden layer and output layer. We will be discussing about approximation properties of RBF networks. If you consider the figure, there is a prototype in each hidden layer. Each neuron here is a prototype. All neurons are able to see the input layer. Whatever the input which matches to the corresponding prototype in the individual neuron, that input will be taken by particular neuron. Here, for example, modulus of x minus xj, where x is input, xj is center of cluster. There are weights given between hidden layer and output layer. Summation weights of hidden layer will be calculated at the output layer. The hidden layer implements radial function as activated function. The output layer will perform weighted sum of hidden units. The input into RBF network is non-linear, where output is often linear. It is used and derived from theory of function approximation. RBF exhibits good approximation properties. The family of RBF networks is broad enough to uniformly approximate any continuous function. That is why it was named after universal approximation property. It can approximate any function. RBF network is very fast learning, as during the training phase, it separates linear function as well as non-linear function. It has only one hidden layer. It uses radial basis function as the activation function. If our intention is not to perform strict interpolation, but we want to perform function approximation, then the optimization is complex, as there is no proper guidance regarding cluster centers. The training is done in two steps. First step is to find cluster center Ti. The second step is to find weights connecting hidden and output layer. RBF neural networks are conceptually similar to k-nearest neighbor models. The basic idea is that a predicted target value of an item is likely to be about the same as other items that have close values of predictor variables. The explanation of unit center goes like: any clustering algorithm can be used to determine the RBF unit center. For example, K means clustering. A set of clusters, each with r-dimensional centers, is determined by the number of input variables or nodes of the input layer. The cluster centers become the centers of the RBF units. The number of clusters is a design parameter and determines the number of nodes in the hidden layer. The k-means clustering algorithm proceeds as follows. For example, the first one: initialize the center of each cluster to a different randomly selected training pattern. Second, assign each training pattern to the nearest cluster. This can be accomplished by calculating the Euclidean distances between the training patterns and the cluster centers. Third, when all training patterns are assigned, calculate the average position for each cluster center. Then they become new cluster centers. Fourth, repeat steps second and third until the cluster centers do not change during the subsequent iterations. There are various RBF type functions, namely linear, Gaussian, cubic, polyharmonic, multiquadratic, inverse multiquadratic, thin plate spline, Mattern. So, we usually use Gaussian type. So here is a Gaussian function. The radial basis function is defined by Gaussian function. Phi j of x is equals to exponential of minus 1 by sigma j square, where sigma j is the measure of width of the jth Gaussian function with center xj. All the Gaussian functions are assigned the same width sigma. In this case, the distinguishing parameter from one hidden neuron to other is xj. So after all, finally, the main drawback of RBF is it requires good coverage of the input space by radial basis function.